Hi everyone, my name is Fedor Chervinskii. I'm Computer Vision Lab lead at Arrival in Berlin. And today I'm going to speculate a little bit about reinforcement learning for industrial robotics. So the connection of Arrival to industrial robotics is very straightforward. Arrival produces electric vehicles, so you can go to our website arrival.com and see some examples. And the important part of our mission is how do we manufacture those vehicles. And we want to shift from building huge factories that produce only very specific models to smaller factories that can produce any kind of design of vehicles. And this can be only done by allowing robots to be much more flexible and the factory itself to be much more flexible. So this requires quite novel approach to robotic operations in general. So first, I'm going to talk about the state of industrial robotics and why does it require the new technologies such as reinforcement learning, then the history of reinforcement learning for robotics, then about existing applications, and the rest of the presentation will be actually going through our slides from our workshop presentation from ICRA this year in June about our experience with reinforcement learning for robotics that we do in Arrival. And we'll finish with some takeaways. What is industrial robotics first? So we can imagine like robotics in general is pretty much obvious. Everyone can imagine a robot. And then there is a very distinct border. Industrial is basically everything which is not consumer. And here you can imagine like consumer robots to be like your vacuum cleaner or grass clipper or anything else like this. But for industrial, the robots basically are in three groups that like two main groups here are AMRs, which stand for autonomous mobile robots. So like on the top image, like the robot that can move itself freely in the space. It can be wheeled robot, it can be aerial robot, it can be legged robot as well. So legged robots are somewhere in between industrial and consumer because we still don't know like all the applications, for example, of the Boston Dynamics spots. So it can be considered both like industrial and consumer. And the second big group is here I put it like NDOF. So like some degrees of freedom manipulators. So like on the bottom images, like very, very typical manipulators that you can see in many factories nowadays in all like most of the major automakers use them. Normally N is from 3 to 7 degrees of freedom. And those are two big groups that like we should talk about when we talk about industrial robotics. So what is the trend right now in the robotics? So on the top left is like the schematic picture of a typical factory for like, I'm going to talk today a lot about automotive because I work for automotive company, but most of it is applicable for any large scale production pretty much. So yeah, I will always refer to automotive industry here, but yeah, this doesn't mean it's only but sort of automakers, they sort of set the trend for other automation, let's see. So on the top left image is the typical conveyor, like basically like a production line, which looks more or less like a conveyor. So it's very linear and there are a lot of robots and they're doing like every robot is doing its particular thing that is sort of hard coded. So every robot knows exactly its trajectory that it should perform, the steps and the exact timing. And the kind of a shift that is happening right now, that people understand that this is not very flexible and not very scalable maybe. So that the new approach that is proposed by many companies that is called like like is a big part of what's considered to be called Industry 4.0 is a so-called matrix approach, when the robots are now placed into so-called robotic cells, right, like on the right image. And each robotic cell, the cells can be more or less identical. So the details can be like deviate, like tooling of the robots and maybe something else, some materials available in the cells. But the cells, they are interchangeable, and the overall production flow is now much more flexible. It can be rescheduled, rerouted. So you can imagine like the material flow is going through the matrix, and it can be dynamically rerouted. And now also what is important, that the flow itself of the materials is not supported by the conveyor belt or any kind of a such hardware, but it is now robots as well. So now mobile robots will be transporting all the materials between cells from one cell to another. And this is important. So on the bottom image, another part of this like paradigm shift is happening, which is like the fixed infrastructure, which was a conveyor belt, is shifting to, first it was automated vehicles, so automated guided vehicles, AGVs, so-called. This is what was the like trend maybe for the last 10 years in warehouses. So basically there are robots that they have kind of rails, then those rails can be magnetic or can be optical, but more or less there are still rails. So the infrastructure supports very limited motion of the robots. And now it is like it's called now autonomous mobile robots. So like from AGVs we go to AMRs, and mobile robots are supposed to be moving freely in the space, choosing their own route. So still there are going to be some rules of the road, and like some lanes and intersection rules and imaginary traffic lights and this kind of stuff. But once again, this is now much more flexible. So it requires AMR to think itself, like so to react to the environment and to able to localize itself. So much bigger requirements for the robot itself. And this is what important for us. So the both parts of the trend, they require now robots to be much more flexible in sort of in terms of operations that they can perform. And now about the reinforcement learning part. So reinforcement learning is like known to go through like sort of a winter that started in 1980s. And it's interesting that even before that winter, so it's in 80s, you can find some papers about like how reinforcement learning can be used for robotics. And after the winter, with the arise of clue learning and like reinforcement learning for video games, for learning from raw pixels, like pretty soon robotic applications started to appear. And the most famous people and actors in this field, they all somehow participate in this, in the reinforcement learning, trying to solve robotic tasks. Those are Abel and Berkeley Group, Levin, Stanford, and Google Brain, and DeepMind, OpenAI, and NVIDIA, that has its own robotics division now. And also, interestingly, there are corporations from the industry world, let's say. Siemens and KUKA, they also participate in this like development of reinforcement learning for robotics. And the problems that typically people are trying to solve, at least in academia, they are more or less the same. So they're about how you manipulate objects with the robot. And also how do you navigate a mobile robot. So regarding manipulators, it's normally some well-known and widespread tasks like grasping and like pick and place task, stacking objects, some other very more specific manipulations with the object. And for mobile robots, it's navigation and reaching the goal given. Sometimes you need to reach a goal that is provided you like in a natural language. This is more like a consumer robotics application, but like Facebook also works a lot in this field. They simulate the task when the robot is somewhere in the apartment and you say like, please go to the to the fridge, and the robot needs to like map the environment and understand what the fridge is and where is it. And one of the kind of interesting, very challenging tasks for control is, for example, a flexible objects manipulation. So, for example, when you have a piece of clothes or a wire or a rope, and you need to do something with this rope with the having a robot with the gripper. So there are certain papers now about this, and the problem itself is quite interesting. So it's hard to simulate and very interesting dynamics. And so the story of the methods is it all actually started normally it's like starting from supervised learning and imitation learning. So you're trying to, so you have some expert or you have something that can show how to do the task, and you're just trying to imitate and generalize and learn to perform the same task by copying an expert. And this seems to be like pretty soon you see that it's not working and it's not generalizing good enough, and then you switch to RL. So then RL, so for example, for the grasping tasks, that was the Google Brain story. So they started this large scale data collection project, which is very like, for me, it's quite classic already. So this is like this kind of pictures you may have seen, where they had like dozens of robots. So the lab is like army of robots. I call it like here Robot Academy, but it seems like there is no such term. I mentioned that. But all those robots, they are doing like the same tasks over and over. They're trying to grasp something from a bin with the like cluttered objects, or they're trying to open a door here, and they just with some heuristics. For example, sometimes they just trying to like, for example, grasp an object, and then you register it was a success or not, and then you collect like tons of this data, and you're trying to in a supervised manner learn what is the successful grasp, and then you're trying to learn how to perform successful grasps. But this turned out to be not very scalable, so they shifted towards like reinforcement learning setup. But like what is showing the biggest success at the moment is actually the combination of both. When you have the reinforcement learning, but you start from some which is called behavioral cloning, or maybe it's again imitation learning. So you have some expert and you have some demonstrations, and like most of the groups that work with real robots and some real more or less real tasks, they nowadays somehow use this kind of imitation learning, so some demonstration of experts, and jumpstart the training from demonstrations, and this allows you to train much faster at least. And also interestingly, people started using representation learning more and more. So when you're trying to, in an unsupervised manner from just not labeled data, learn some representation. For example, if you want to train a controller which will take an image as input, so you can train some encoder first before actually training reinforcement learning agent actor. And also sim to real is quite important, so we'll show how it works for us. So when you use simulation a lot, like heavily for domain randomization and training in simulation, and you're trying to transfer it to the real world. So about existing applications. So actually, very interestingly, so at the moment, I would say, like, again, this is as far as I know, but there is only one company that is known to be doing something which is more or less real. So they deployed their applications to the real sorting center in this case. And it's called Covariant AI, and it's being led by the well-known Peter Abel, which is again the professor of reinforcement learning in Berkeley. And but there are question marks because it's actually not very clear if the thing that they deployed that is working. So I don't have a video here, but there is a robot which can grasp. There is a vacuum gripper, and it's given some arbitrary objects in the box. I need to grasp those objects and sort them into other bins. And grasping is basically sucking with this vacuum sucking cup, like vacuum gripper. So the whole task is how to choose an optimal point for the gripper to suck to an object. And it looks pretty simple, but seems like for them it's been a lot of challenges. And they mentioned on their website that they do a lot of reinforcement learning. They affiliated a lot with Berkeley, and I think all of the co-founders are from his lab. But they actually don't explicitly mention if the thing working on the robot is reinforcement learning trained or not. So they just mentioned that it's machine learning, but I expect it to be something, again, hybrid. So we don't know explicitly. Yeah, and when I've been like searching through like all the other companies, there are only research projects at the moment. So, and it's pretty much the same for our company. So today I'm going to talk about our research project, and we still have high hopes that it will be like any time, not very soon, but it will be moving towards kind of production pipelines. But still right now we should be honest that this is a research project that we've done in our lab in Berlin. And this is how we presented it in ICRA. So it's the project called Sim2Real for peg hole insertion with eye-in-hand camera. So many like specific terms here. So for Sim2Real, I guess you already know what it is. Peg hole insertion is classic task for robotics, for robotic assembly, when you're trying to insert something into something. And eye-in-hand camera is when your camera is mounted on the manipulator and effector. This is also like this slang name for this kind of scenario. And we start from the results. So here is the working like policy deployed on the real robot. So here you can see what is the peg, what is the hole. And on the left is like the snapshots, like each frame is actually one state of environment. And on the bottom is observation of the network. So here the network, the policy network is working solely on the image, which is also grayscale from the camera mounted on the end effector. And the output of this network is like where you should move to successfully insert the peg. And on the right, you see like moving in the steps. So it's actually steps of the actor moving in real time. And you can see some interesting stuff that the insertion does not happen like straightforward from top down. It's actually going some strange trajectory. And if you look at the image, you will notice that the trajectory that actor is choosing is such that you see the hole most of the time. So you don't cover the hole with the peg right away. So you start to move down a little bit like shifted, and you adjust in the very, very end. So you till the last steps, you see the hole. So it helps you to orient. This is how we like interpret the policy. Maybe it's not that smart. Maybe it's just a coincidence, but we like hope that it's actually the result of the training the controller end to end. So this is not just a stupid reactive like where to move right, left, top, down. Because it's trained end to end, it can sort of have a kind of a strategy, let's say. So what is the motivation of doing that? So as I said, we are targeting like a flexible manufacturing, and for flexible manufacturing, it means that the every time the robot receives some parts to one insert into another or something else, there is a lot of uncertainty about the parts themselves and about where they're placed. So we are here trying to resolve the uncertainty of parts placement. And the straightforward way to resolve that is to have external pose estimation, to have, again, like computer vision that will tell you exactly where the parts are. But this can have some problems. So there are errors, there are occlusions, there are some problems because of the like multiple transforms of between coordinate systems. So if you transform from camera coordinate system to the world coordinate system, then back to the robot coordinate system, so you have like all the errors summed up. And we just asking ourselves, like, can a maximal precision closed vision control loop be trained? So if we really, the robot, the end effector that is doing the insertion, like estimating the relative position and reacting on that directly. So we're trying to like collapse all the errors into a single thing. And why training? Like, why machine learning? Like, obviously because we are lazy, we don't want to do much programming, but like just want to leave it and it will train and will do the thing ideally. So we want, like, with every new scenario we need to solve, we don't want to write down like new heuristics and new algorithms, new controllers. So the experience setup we have, we chose like peg hole is just a good approximation for some real tasks that you may have, like screwing or insertion. It's like good model experiment. And Einhand is, I think we think that it serves best for our idea of direct visual feedback, because if you place the camera outside, like you can imagine, like if something is moving in the image, then it's like a small percentage of image will change and your agent need to like really have some kind of attention. But if you place the camera on the manipulator, when you move the manipulator, your image changes dramatically and you can have a good idea of where are you moving and how, like what is changing, and you're looking exactly on where things are happening. And this is also like the closer you look, the better you see. So your resolution increases towards like the most critical part of the task. So that's why we chose a simulator, which is called Capella Sim. Is like specialized simulator for robots of such kind. And for real environment, we have like the same robot, CUR5E, Universal Robotics, and into real sense, but we actually don't use depth, but just use it as a normal camera. And for comparison, we also implemented like a visual surveying baseline. So we just implemented some heuristics based on the task. So very specific for the task that will detect a hole and move the peg towards the hole. And we just like to have something to compare. And yeah, so on the bottom, you can see like how the baseline is working and some like OpenCV tricks. It's quite successful, but doesn't look very flexible as if you look at the implementation. Yeah, so on the right, you can see like how the training could look like. Here we don't have a gripper, but it's actually could be important that the gripper looks like in the real world, and some TensorFlow graphs and some details, like technical details you might find interesting. So the observation is basically RGB image, and the rest is turned out to be not critical. So we thought that depth would help a lot, but it doesn't. And we also thought that the proprioception, like joint position, will help a lot, but they don't. And like also we have some kind of a bit of domain randomization, which helps. And like policy is a quite simple convolutional neural network. And for training algorithm, we chose TD3. So obviously we started from DDBG because we have continuous control, and we want to do off policy because we want to be don't want to train for long. And we also tried autocritic, but it showed somehow worse results. So we didn't spend too much time on tuning the hyperparameters. So TD3 after all worked best for us. And what's important here, important to mention, yeah, we used Catalyst to play with different algorithms and their hyperparameters. And it was really, really helpful along the way. So the overall success story of our integration with Catalyst you can read in our Medium blog that we recently showed. That is now in PyTorch. And yeah, so for the action space, we constrained ourselves here to 3D, but it can be actually extended to 6D. But here we move the robot only like in X, Y, Z. And for the reward is also a kind of interesting story. So we started from like shape, like given a reward for everything. So it was like the most obvious idea here is to have a like smooth reward for distance. And it's here like any distance you travel towards the goal, you being rewarded proportionally. But also we wanted to add like reward for success state reaching, some like a sparse reward, some negative reward for collisions, and also like negative reward each time just because like we want to finish earlier. But it turned out that you can like do as well with just having the smooth distance reward, so it does all the tasks. And here on the graphs, you can also notice that the like robot really fast learns how to reach the mating part, but not inserting. And the insertion happens like sometimes randomly, and then after sometimes experiencing the insertion randomly, the agent learns to like consistently insert every time. So the takeaways of this particular experiment was like quite interesting. So the proprioception is not required, so the image can be enough. So it can be even important because like proprioception is like absolute. So it's an absolute frame of the robot, but the image is also always relative. So you can start in any part of your table, and you just need to move relatively to the goal. And in terms of proprioception, it can be very different states, but in terms of image and in terms of required motion, it's going to be all the same. So we also experimented a lot with depth from stereo, from real sense, but it showed to show very specific kind of noise. And you can see it on the right top image. So the real sense depth is very noisy. And when you start training with the depth in simulation, the depth in simulation is obviously much better. And you need to really specifically simulate this very specific kind of noise, which is like very challenging task in itself. So we decided just to abandon using depth. And we also learned that calibration, like the camera to end effector calibration, is very important. So to close the sim to real gap, obviously, and then yeah, some numbers. So how much does it take to train on GPU? We still experience a lot of illumination sensitivity. So this is just, yeah, we just understand that we need more domain randomization maybe. And also very interesting stuff that we trained it on the peg, which was like 1 centimeter smaller in diameter than the hole. And then we just changed the peg to be bigger, and it somehow inserted again. So like maybe again, it's happy coincidence, but seems like it generalized to align the peg to the hole. It doesn't really depend how big is the peg with respect to the hole. And as I said, like we also it looks like the controller is optimizing visibility of the target. Also, that there is a strategy to always approach the hole from the side, which makes the situation more visible. So yeah, so this was the project, but the project like showed some kind of success, but we still see that is very hard to. Still, it took a lot of time to tune the hyperparameters, to set up the environments, also to really manage the sim to real transfer. And looking at the industry, we see that there is still seems like 2 to 5 years to see this to be applied to the real factories, but we still hope that like we will take active part in that. And but also another good trend that we see, that more and more complicated and domain-specific environments is appearing. So, for example, for this Capella sim simulator is recently the RL bench framework was open sourced, which is like actually a lot of different environments with the robots that need to solve like some tasks like open a cabinet, like or pour water into a bottle, into a glass from a bottle, like this kind of tasks. They are being now just open sourced as new gym environments. And I think like the more and more this kind of specific environments we'll see, the more and more we will see some kind of meta learning and this kind of hybrid approaches from demonstration to reinforcement learning to be more and more applicable to more complex and real world tasks. And also regarding meta learning and this kind of trending topics in reinforcement learning, we see that there is also a lot of work in this direction on how do you ship your something that you trained on simulation, for example, to real world, and how do you reuse the models that you have trained for different tasks. And this looks very promising. But the initial problem that we tried to solve, that like we thought that it's going to be easier to train than to program, that is still doesn't hold. So it seems like it's still easier to program a robot to do specific particular tasks than to train it to do it, hoping that it will like generalize to all other tasks. So yeah, this sounds maybe not very optimistic, but we are optimistic, and we really see a lot of progress happening in the academia, and we see some movement in the industry and from the industry, from the companies like Siemens and KUKA also experimenting in this direction. So we really hope that we will see more and more applications of the reinforcement learning to industrial robots in the future. So thanks for your attention. I'm happy to answer your questions.